Let's move to the third section. Concentration-dependent diffusivity, which means that the diffusivity is not a constant anymore. It will change with concentration. So in order to get how or understand how the diffusivity change with concentration, we are going to introduce the Boltzmann-Montana analysis to help you to obtain the diffusivity. And at this moment, probably some people will ask, Professor, how to recognize or how to know in my interesting materials whether the D is constant or not, or it change with concentration. So the most simplest way is you can, when you need to perform an experiment, for example, like for example, we have a diffusion couple A bind with B, and we have an interface in between. And you, in the beginning, you can heat these materials up and allow diffusion, interdiffusions happens. And at your interesting time point, then you can stop this diffusion process. Then you do the section to understand or get the concentration profile for A materials. If then you can try to plot how the concentration of A atoms change with location. As long as you get this like a symmetry arrow functions, 这对称的 arrow function profile 的时候，which imply that in this system the diffusivity equals to constant. But however, if you get this profile, show in blue, this profile is non-symmetry. It's a asymmetry or non-symmetry for the arrow function, this profile, which tell you that your diffusivity change with concentration. It's not a constant. It will change with concentration. But this profile, you can image that. We can observe that the at higher concentration part, high concentration, which means we have a high concentration of A atoms. It turns out like it moves shorter than the A atom at the lower concentration site, which means that because you can observe that the A atom can penetrate deeper. So in this case, probably this function implies that the diffusivity is higher at low concentration part compared to at higher concentration part. Okay, so just for reference, and this red line, which means that also we can have a plan, mathematic plan to for this case to allow the atoms move to right-handed side will be equals to the atom move to right-handed side, which means that these atoms actually they disappear, which means that they move to right-handed side. So this plan allow this area equals to this area. This is we also call it as M is a Montana plan. This is a mathematic plan, which means that it's not a real plan. You can visualize or you can label it. It's just a mathematic plan. 所以在这里的话，有个很重要的是说，大部分比较多同学会问的是说，如何知道说，在我有兴趣的系统里面，我的diffusivity 是不是 constant？所以你就最简单就是你做一个实验，然后那怎么做实验呢？其实就像刚刚讲的，你可以就我们现在画的例子，它是一个 diffusion couple，那你就可以把温度提高，然后让 A 原子扩散到 B 的到右边这个部分，然后在一个特定的时间点，你就喊停之后，你就把这整个 sample 拿去做 section，然后 try to plot，你就 plot 你的 A 原子的 concentration profile as a function of location。那如果它是一个对称 arrow function 对称的，像这个绿色这条线左右对称的，那就是告诉你说， 你的 D 其实是 constant，然后其实它 D 的 constant 的意思就是说，你的材料不管在哪个浓度的时候，它跑的速度都是一样的，所以它会得到一个左右对称 error function 的 profile。但如果不是，就像是蓝色这种，就很明显它是一个非对称的。也就是说，这边失去的原子很明显，它们跑的距离比较短，然后这边原子跑的比较深，所以就可以发觉到说，原子在高浓度的地方看起来跑的比较慢，然后在低浓度的地方它跑的比较远。那这种如果是非对称、对称的 error function 的时候，就在暗示你说你的 diffusivity 事实上是会随着浓度而改变的。那当你遇到蓝色这个 case 的时候when you recognize that or you notice that your diffusivity is not a constant, it changes with concentration. Then you need to have an analyze tool to help you to obtain how the D change with concentration. So this is the analyze method we are going to introduce to you. We call it Boltzmann-Montano analyze. So this is the diffusion equations, and this is the materials we just show you is we have A B diffusion couple, and we use the green line to plot the concentration of atom A before diffusions happen. So we will get this step function. And before diffusions happen, so we need to have a boundary conditions here listed on this slide. For example, like a concentration of A atom equal to C0, and at infinity, negative infinity, the concentration gradient does not change with. We don't have concentration gradient. And for your right-handed side, which is positive infinity, at positive infinity, also there's no, no concentration gradient, no flux of atom A. Okay, and in order to allow the diffusions happen, and I know this curve actually is a symmetry of the error function. It's not a real case we are going to discuss, but I just use this to represent just an example. Be specific, it should be a symmetry, right? Okay. So next, in order to get how the diffusivity change with concentration, so we need to solve this differentiation equation. And do remember that how we solve this the diffusion equation before in prior slide what have a look here, slide 9, page 9. We introduce the dimensionless variable iota to help you to get the convert it to ordinary differentiation equation, right? But now you cannot use this iota, right? Because inside this iota you have a D, but as we mentioned in this case, the D is not a constant anymore. So at this moment, iota equals to x divided by square root of t. This will help you to solve this differentiation equation. So we use the iota equals to x divided by square root of t. Because we want to know the results D, so you cannot put a D inside. So after series deviation, you can get the D of C prime, which means that at any concentration of atom, at any at C prime, concentration C prime, then you can get these results, and can be simply classified into 3 parts, which means that can change. Diffusivity will change with these 3 parameters. But how to get the how to use this variable iota to get this differentiation, to solve this differentiation equation, and finally get this results to get the D. The detailed deviation will be shown in next slide. So how about probably we can just quick go through this, then I will explain more about how the D change with concentration. But how to get this how to solve this differentiation equation? Because we introduced the variable iota, and so on your left hand, our final goal is converted the partial c partial t to partial c partial iota, and also partial c partial x. I hope I also want to get the partial c partial iota. So everything will be converted to partial with iota. So this is our final goal. So for left-handed side, use the same chain rule. So you can help you to get the partial c partial t will be equals to the here. And on your right-handed side, the easiest way you can use is I'll just copy here, but dx, if you you take the derivative with this equation, dx divided by square root of t will be equals to d iota. So I use the d iota times square root of t to substitute dx. So I got this to substitute dx, and this dx also use this d iota square times square root of t to substitute this one. So on your right hand side, I got this result, right? This result can help you to, sorry, this result you can take the parameters square root of t to outside. So I got the t. And here we have t, right? You can delete the t because this will be equals to here, right? This is left-handed side, this is right-handed side. So let's t delete. And now the rest of is what you have is you have the the differentiability dc over the iota, and outside you got the partial with the iota, and on your right hand side you got here this, right? So you have here and here, but I can delete the same term out. So the rest of part I got here, right? This term and this term, I just take the integral for both sides. And integral from where? From for the concentration will be from concentration in this figure is y axis. So integral will be from 0 to c0. Will be here to here, but I'm not just want to know the how the but I'm interested to understand how the differentiability change with c, different c, right? So instead of use the c0, I use the c prime. C prime can be any concentration ranging from 0 to c0. So I got the bottom limit is 0 and upper limit is c prime. So the same idea, c0, c prime. Integral here, so I got this. Then I converted the iota back to x divided by square root of t. And this turn, I just copy them. And I've realized that realized that the d is interesting. I want to obtain the d. How the d change with c, right? So here I have a square root of t on your left-handed side also. So I move this back to here, move to left-handed side. So I got a t. Here is t, right? So you got 2t negative term here, and you also got the integral term. Copy here, integral term. And the only thing left on your right-handed side is here. So I move to left-handed side will be the reciprocal of concentration gradient at C prime because it's at C prime. But so now I got finally I successfully to get the D of C prime can be expressed into show it here. So as long as you list any concentration C prime, then you can get the D equals to what after serious calculations. 所以在这里的话，简单来讲就是，这里你要解它的解，那我们可以参考前面的推导，我们的前面推导是 X3 根号 4DT 嘛，但那个时候 D 是 constant，所以我们可以把它放在这里。但在这里的话，D 是你想要求的，所以这个时候的 variable 就只剩 T，那你就把它带进去。那左边就用 chain rule，右边的话就推荐大家用这个，然后到最后大家就可以发觉这个 T。两个 t 可以被提出来，跟前面的 t 消掉，那你就可以得到这边。然后这边的话就两边做积分。那积分的话就是积谁呢？因为这里的都是底 Ca 嘛，就是对浓度。因为其实我们最想知道 D 是如何随着浓度而改变的，所以积分的话就会从浓度就会从0到 C0。但因为你想要知道是每一个浓度它的 D 怎么变化，所以我们就不会用这个固定的 C0总浓度，而是我想知道在中间这个浓度是多少，用 C prom，所以就会这边就会经过推导完之后就会这。然后在这里的话，大家要记得，因为它这里是积分，然后 C prom 减0，那0的时候就没有浓度，所以这个值会是0，所以后来左边这边就会是 diffusivity at C prom。So we can, based on these results, actually this result is identical with this one, but let me explain this results. So diffusivity will change with concentration and will change by what? T is time. So if you change with time, so if you increase the diffusion time, then diffusivity will decrease. Okay, so sorry, probably we use this. And the middle part, or probably we can see the last part. The right-handed part actually is the integral part. Integral what is integral from location times the concentration of A, an integral from 0 to C prime. So for example, if you're interested in, here, this C prime, this is C prime, then this means that this is C prime, okay? So integral, this x will be times the concentration at this moment Ca equals to 0, so it's 0. But I will sum them together, so you can see this blue region integral until here C prime. So this term is, you sum this term up. So you got the integral from C0 to C prime, then you got this value. And the middle part is the slope at C prime, the slope at C prime, but it's a reciprocal of the slope at C prime. It's a middle. So the diffusivity, as long as I know the C prime, then I can use these figures to get, because the diffusion time I know, and based on the C prime you're interested in, then I can integral here, and also I also can get the slope, then I can reciprocal of the slope, right? But the most important thing, I believe you have noticed that in order to get the D of C prime or of C, you need to plot the concentration profile at your at specifically at indicated time point. Then that can help you to get the integral term and also the reciprocal of the slope term. Then you know this, and you know the diffusion time, then you can get D. 在这里的话就很重要，就发觉说，哎，我经过我计算之后，D 事实上主要分成这3个部分，会影响到我的扩散系数 D。第一个是时间，扩散时间，时间越长的话，那我的 D 会越小。那接下来要分享的是最右边这个 term，那最右边这个是个积分 term，它是位置对上浓度积分。 那浓度的话是 Y 轴，所以我是从零积到可以积到 C prom， 哦，可以积到 C prom。那 C prom 就是我讲的我有兴趣的这个浓度嘛。那这个积法的概念就是这个积出来的值就是这个 profile 这样一直积，因为就是一个距离乘上 x，像这个是 x，这个是 x，然后这个浓度是零，所以你就积。那这个的话，这个距离是多少？然后浓度是这个，然后就积。那在这里的话，这一绿色、蓝色这一项就是积到这里的所有的值，然后中间这一项就是在这个点上面的斜率的导数。所以从这里就可以知道说你如果真的要知道 D 的话，很重要的一件事就是你需要有这个 concentration 的 profile at diffusion time t。所以只要你有这个 concentration profile，你就可以算出 D of C prime。那你可以预期说，你的 C prime 也可以是这里，就是每一个都会不一样，对不对？然后接下来就会有人问的是说，那老师可不可以粗略的告诉我说，哪一项影响 D 最大？那我们来可以看一下这个 diffusion 的时间，通常你喊停，它就是已经停了嘛。所以那接下来就是这两个 turn 哪个影响 D 越大？那这个的话是一个积分 turn，积原者数目，所以它差一点点，从这里到这里可能就只差1 mm。但是斜率，大家看斜率，其实斜率差一点点就会差很多，所以很重要的一个关键，事实上中间这个 turn 会是主导这个 profile 的斜率，会是主导 D 大小的很决定的关键因素，而不是积分这个项。那当然你不能比这个地方跟很远的地方让积分差很多，我指的是当它们的浓度没有差很多的时候，可能会是由斜率来做主导，可以吗？OK。So this term, slope, I mean reciprocal of the slope, the value of the slope play an important role to determine the magnitude of the diffusivity. Okay, so it's quite important. So that's and next, probably some people will question about Professor. It turns out yes, you can successfully to get the D at specific CPROM, but if you want to integral, you need to set the bottom line x equal CA equals to 0. But sometimes how to locate x equals to 0? Oh, where is x equals to 0? Then that can help you to get the D, right? X equals to 0. So how to locate that? As we learned before, actually the as long as we need to locate the x equals to 0, but as we need to learn how to locate x equals to 0, the point at x equals to 0. Then that can help you to get this integral term, then slope term, and also get the, as long as you know the diffusion time, then you can get the D, right? But when D equals to constant, these figures will be symmetry. It's easy. The interface equals to, at the interface, the x equals to 0. But now the D change with time, which means that the plot, the real concentration profile you have will be shown like this. And the interface is no longer the point, the location at x equals to 0. So now we need to find the mathematical plane, which we call the Montano interface. This is the plane at x equals to 0. So this is a typical profile you should have when you figure out that D is not a constant anymore. You should have a symmetry profile, concentration profile. Probably will be shown like this. But how to locate this Montano interface? So I will introduce what's the Montano interface, which means that the quantity of A atoms moves from removed from A side will be equals to the quantity of the atom ended into B side. So this atoms removed from A side should ended to B side. The plane is we call a Montano interface. And this plane is not a real plane, which means that you can visualize. You cannot visualize, 你不能看到它. This is just a mathematically defined plane. Okay, so how to locate this plane? So based on the equation we derive here, I just copy the equation from previous slide. This is iota, right? And I put the iota back here. So I just copy here. And as you learn, we need to integral along the concentration. Here it will be Cb from 0 to C0. So from here to here. And from this is 25%, but is C0. After integral from this x times the concentration, x times concentration, integral here, and at as long as you know x equals to 0, then here will be the negative term, right? So positive area plus negative area should be equals to 0. So this plane we call the Montano interface. This plane across which the net flux equals to 0. So after, this, I converted it back to here. So this equation will help you to get this plane, x equals to 0 plane. Okay, so as long as you need to locate, you need to use this equation to get this plane, then you can get here this term, and also this term. So this is quite important. You need to locate the Montano interface first. Then you can get the diffusivity. So I'm just give you a quick review here. How to get the D change at a specific concentration. First, you need to perform your experiments and get a concentration profile at a specific diffusion time T. Then, find the Montano interface. Then, as long as you know this one, so you can have this term, you integral, then you need to tell me what's the C prong you are interested in. If here, then you can integral here to here. And also this term, right? And you also take the slope, reciprocal for a slope. You will know here, then you can get a D at this concentration at CP of CP. OK，所以在这里的话，很快再提醒一下大家说，如果你要知道，就是你要知道你的 diffusivity 在特定浓度上面是多少的时候，第一件事情是你要先做实验，然后在你知道的扩散时间之下，把 concentration profile 画出来。然后接着，为了得到第二项跟第三项，你需要知道 Montano interface 在哪里。就用这个公式，然后或者是用图纸，这个就是你要用这个公式来求这个 x 等于0这个平面在哪里。一旦你定出来之后，你才能知道，你又知道你知道的，你想有兴趣的 C prime 假设在这里，那这里可能是7% 值附近，那你就可以第三项就是从这里积到7%，然后中间那一项就是这里的斜率的导数，你就可以知道。OK，好吗？那 so let's move to next slide to see the to give you an example here. So when we deal with the concentration dependent diffusivity, we assume the interdiffusivity D, which measures the interdiffusivity between A and B elements in the laboratory frame. We learned this before. And it's a strong function of concentration B, which means that diffusivity change with concentration B. Given the diffusion couples here, which is annealing at high temperature for time t, how does the interdiffusivity change with Cb? So you can get this concentration profile after time t. You section these materials and try to plot the Cb as a function of location. And you find this, what did you find? Did you find a symmetry error function or a symmetry error function? It turns out it's asymmetry error functions. And especially we find that at lower concentration of CB region, it turns out penetrate deeper, right? So it should have a larger diffusivity. But at higher concentration part, it turns out the atoms moves smaller or shorter. But you can double check, right? Because this slope is smaller, but reciprocal of the smaller value, we got the larger one. So we got the larger D. But here, the same idea, even we got the larger slope, larger value for the slope, but reciprocal for larger value, we got a smaller. So after you got a smaller D. So as we mentioned, larger diffusivity, you can visualize B atoms penetrate deeper compared to at the higher concentration CB. So just a quick review here. When you visualize the concentration profile, show the symmetry error function, which means tell you that the diffusivity equals to constant. But when you figure out that the concentration profile shows a symmetry, then it tell you that your diffusivity change with concentration, and you need to explain or analyze how it change with concentration. Okay, so and you also can further to figure out where the Montano interface is by integral here to here, and you can get equals to 0. Then the 0 x equals to 0. You can find this plane will be the Montano interface to allow this area equals to this area, which means the A atoms removes to B side will be equals to the atoms move into the B side, okay? Remove from A side will be equals to the atoms move into B side. 在这里的话，就是简单复习一下，所以你要知道你的材料的 D 是不是 constant，就是在特定的时间点之后去 section 之后去画出 concentration profile 就可以简单的知道了。那在这里唯一的提醒就是 Montano interface 事实上是一个数学的平面，它只是想强调这个原子数跟离开 A side 的原子数应该要等于进入 B side 的原子数。所以它是个数学平面。数学平面意思就是你看不到它，就只是个数学平面，可以吗？Okay, so we simply ended the third sections, so we are going to move to the fourth section. An isotropic diffusivity. As we mentioned before, some parameters will affect the diffusivity. And we have mentioned about the temperature will affect the diffusivity, and also the time also probably will affect the diffusivity, right? For example, like this, time will also sometimes will affect the diffusivity. But here we want to show, give you an ideas about crystal structure also will affect the diffusivity a lot. For example, like we have a cubic, which means that alpha, beta, and gamma equals to 90 degrees C. This we call a cubic structures. The diffusivity for cubic structure, usually in this crystal, we call isotropic diffusivity. Not really isotropic, but compared to this one, because when this is alpha, beta, gamma equals to 90 degrees. But for the other case, for here, probably it would be triclinic case. This is the alpha, beta, and gamma not equals to 90 degrees C. In this case, just want to highlight this case. Both this crystal structure will significantly affect the diffusivity. But how it affect? Give you an example here. Sometimes we will have an isotropic crystal structure like this. This is quite typical. That will lead you also have anisotropic diffusion properties. For example, like the graphite, the thermal conductivity on the plane is around 355, is much larger than the thermal conductivity across or perpendicular between two planes. So let's tell you that graphite belongs to anisotropic crystal structures. For isotropic one, the diffusivity, some people use the scalar 存量 to represent the diffusivity. But when you deal with anisotropic crystal structures, you need to, which means that you have like a different diffusivity along different axes. So people will use the diffusivity tensor to represent their diffusivity in this like anisotropic crystal structures by using the 3 × 3 diffusivity tensor. So based on you have different diffusivity along X, Y, and Z, so you will get a different flux along X, Y, and Z. So when you write down the flux along X, then you can get this. And if a flux along Y02, you will get this times this times this, then plus this times this, and negative term. And the last one will be the same idea. This times this plus this times this plus this times this, and don't forget the minus 10. So when you deal with an isotropic structures, as long as you can formulate the diffusivity tensors, that can help easily to get the Jx, Jy, and Jz along different axes. It's not a big problem, but you need to have this idea. You need to know, as long as the crystal you deal with is not isotropic one, you need to formulate the diffusivity tensor to explain or express your case in your case. Okay, so we want to talk more about the diffusivity tensor. This is a 3 × 3, so some people probably will think about like a 3 × 3. So we have a 9 unknown parameters for diffusivity. It's so complicated. So based on the Ansaka symmetry, you can reduce the unknown parameters from 9 to 6. We will assume D21 equals to D12. So we use a D12 to represent both. And D31 equals to D13. So we use D13 to represent this. The same idea, D32 equals to D23. We use a D23 to represent them. So under these situations, we successfully to reduce the unknown diffusivity parameters from 9 to 1, 2, 3, 4, 5, 6, 6. So it turns out like if you deal with isotropic crystal, then you use the scalar. If you deal with anisotropic one, you need to have the diffusivity tensor. But could you? I'm going to give you some case. Under what kind of conditions we have the isotropic crystal? For example, like the cubic structures. For example, like FCC, simple cubic, body center cubic, and diamond cubic. The diffusivity is a scalar because A equals to because a cubic structure, which means that the A equals to B equals to C, and alpha equals to beta, alpha, beta, gamma equals to 90 degrees C. So under these situations, you have D11 equals to D22 equals to D33, and the rest of the diffusivity equals to 0. So this is we call the isotropic materials we have. But besides the cubic structures, some people probably will mention about tetragonal, hexagonal. That's slightly different. For this case, actually, like A equals to B, not equals to C, but they also alpha equals to beta equals to gamma, so like equals to 90 degrees So the diffusivity is D11 equals to D22, not equals to D33. Because A equals to B, not equals to C. So we only have here, and the rest of diffusivity equals to 0 because the three axes also perpendicular with the others. 所以就是如果是要等项的话，那就是要是 cubic structure，因为它 A 等于 B 等于 C 嘛，然后三轴又是90，互相要加90度。所以我的 diffusivity 可以就是沿着 x、沿着 y 跟沿着 z，然后它们三轴，它们三个的间距 lattice 的那个 constant 又一样的话，那它们三个就一样，所以我们就常会用一个定值，一个值来表示它们。所以过去在一些题目里面，如果你看到第一，它就只讲一个村，就是一个数字，它没有特别讲哪个方向的话，通常那个材料它就暗示你说那个材料事实上是 isotropic 的 structure，就是一些像 cubic structure 这几个面心简单面心、体心跟钻石结构。但另外一个是 tetragonal 或 hexagonal 嘛，那他们基本上也是三轴都是90度，然后但 A 等于 B 但不等于 C，那就是大家可以知道，就是间距不同的话，我原子移动的速度就会不一样。这详细第4节会再说，但从这里就可以知道 A 跟 B 的 diffusivity 会一样，C 会不一样，但他们都是90度，所以这些旁边这一堆都没有。So belongs to anisotropic and orthorhombic crystal, all angles equals to 90 degrees, but A not equals to B not equals to C. This implies that we have DA, DB, and DC. So we have D11, D22, and D33. All the angles, all the axes are perpendicular to others. So the rest of the facility equals to 0. And if you have monoclinic, which means that A not equals to B not equals to C, and you have alpha and gamma equals to 90 degrees C, but beta not beta. So it turns out your beta is Y, right? So which means that you have D13. Okay, we got D11, D22, and D33, and also we have D13. Okay, and for triclinical ones, it's complicated. A not equals to B not equals to C, which means that you have for sure you have D11, D22, and D33, and all the angles are not equals to 90 degrees. So which means that you also have the rest of diffusivities. You have a 3 times 3 diffusivities and six unknown parameters. It's so complicated. But your textbook also highlight that under this complicated like triclinical systems, there's a way to simplify uh, the diffusivity tensors from this 3 times 3 down to uh, down to here by converting the assets from original system x1, x2, and x3 to principal systems. Then, which means that you just converted the three assets to this principal into principal systems by what? By using like as long as you can successfully convert it to here, then you can easily to write down their diffusion equations. But some people probably will ask how to do this conversion by solving the eigenvalue for this diffusivity tensor. Then as long as you got lambda 1, lambda 2, and lambda 3, so you can get the D11, D22, and D33. So this is the final results. This just give you like a quick view or brief introductions how to deal with this complicated diffusivity tensor in triclinical systems. There's also by solving the eigenvalues, then you also can simplify them into principal systems. Okay, so this is why you need to learn the eigenvalue before to help you to simplify this. This is applications for learning the eigenvalue part. Okay. Sorry, so I'm going to give you some quick summary here. So interdiffusion analyze can as long as you in order to know whether you need to perform the Boltzmann-Montanaro analysis, you need to perform your experiments to have the concentration profile to help you to recognize whether the diffusivity change with concentration or not. Okay, then you can like make a decision to determine whether you need to use Boltzmann-Montanaro analysis to help you to get the D at a specific or your interesting concentration. And the other important take-home image message would be that, and when you have anisotropic crystal structures, for example, like tetragonal, besides all the cubic structures, the rest of them you need to formulate the diffusivity tensor for them. And under that case, we will say you have the anisotropic diffusivity. OK，在这里的话，最后的summary 其实蛮简单，也就是说，今天讲的这几个其实都是一些 spatial 的 case。在简单里面介绍一些跟真实有关的，也就是说，在过往大家觉得第一，扩散系数会是常数，但现在这礼拜就教了一些，告诉大家说，当你发现你的扩散的 profile 不对，不是 error function 对称的 error function 的时候，那你就要知道你的 D 不是常数，然后就可以用 Boltzmann-Montanaro 的 analyze 来帮助你知道你的 D 是如何随着浓度而改变的，这就是这个。然后接着就是过往我们在任何一个题目给你 D 的时候，它通常都是给你一个 scalar，就是一个存量。但其实它就是在暗示你说，现在这个材料，不管是铝或者是什么材料，它事实上是 isotropic 的材料，那它的三轴都是 D 都是一样的，所以它就没有特别说，它只给你一个 D 的值。但你自己要知道说，当你的做的实验的材料如果是 an isotropic structure 的时候，像 graphite 或者是其他 tetragonal 或者是其他monoclinic hexagonal 这些其他的材料的时候，你要记得你的 diffusivity，你要写出 diffusivity 的 tensor，可以吗？那因为他们是就是会是3乘上3的，那会依据就是不同的状况，然后 D 会不一样，就给大家做补充，好不好？So let's end it the lecture 3 here.